I will talk about the topic in quality control, and it is about circular economy, so mixing these topics of the show together. One of the problems that we are very focused on when it comes to quality of recyclates and quality of products is we're dealing with unknown material. You buy a recyclate, it's a PP, and you know potentially there's a contamination in it. Or you even buy a cheaper recyclate that already says PE-PP mix. So it's really a bottleneck that you buy a material and you don't have, like we're used with virgin materials, you don't have a data sheet that tells you specifically what's in there. And there's always a question mark if you have a data sheet, if that's correct. So a lot more needs to be done in incoming goods inspection than we're used to with virgin materials. Small shifts in the composition can lead to big effects and process and the properties. Failures, catastrophic failures, obviously the thing that we're most afraid of. And that's why a lot of people, in my opinion, shy away from using recyclates and getting into it because it's this big unknown. What will happen? How can I control it? And this lack of understanding of quality and that quality control is important really creates problems in adopting recyclates. We are producer of analysis equipment for the polymer industry and other industries, but for the polymer industry, I can say it, I come from research, so I'm very familiar with all these techniques, and a lot of plastics processors don't use any of them because they can trust the data sheets. So it's a big shift in adopting quality control as something that everybody needs to do. The methods that people already know and rely on is melt flow index. Everybody has used it. It's that one metric and that one instrument that more or less every processor that I've worked with has. But it's a single point value, and you even go to a supplier of recyclate and they ask, what MFI do you want? And then they put modifiers and all kinds of junk in it to give you the MFI that you're asking for, but it might not have the properties that you're actually looking for. The other technology that is frequently used for identification of plastics is FDIR, or infrared spectroscopy, but that has problems with dark materials, multi-layers. So what we see as a manufacturer of DSCs, differential scanning calorimetries, that's what the industry is looking at. The result that you get if you don't understand the quality is downgrading, over-engineering, so you have a lot of angst around it, or complete rejection of recyclates, that OEMs don't even put it in their specifications. And that's costing us material, energy, and credibility. Because in the end, use of recyclates that isn't done well will ruin the industry for the rest. So we are using our well-established DSC technology that a lot of people know in quality analysis of polymers, and make it more intelligent. Obviously, that's the topic of the day, Smart Saturday, and using AI to make it even better. And I want to talk today about what's behind the AI solution or the machine learning solution we created, and what it can and what it cannot do. So DSC, you don't need to understand DSC in the talk. I can assure you I'll try to make it interesting for those of you who know DSC and those are just interested in data. So DSC measures how a polymer melts and crystallizes and gives us the thermal fingerprint of the material. AI is then used to organize the variability that we get in DSC data and separates overlapping peaks when you have mixtures. What it doesn't do, it doesn't fix bad data or bad labels. So it's this principle of garbage in, garbage out. What we've created, what we launched at the K-Show, is a software, we call it Proteus Now Quantify. So getting a quantity. It's a software that can identify and quantify the composition of an unknown polymer sample. So how we started, Raphael had already mentioned the book. It started 10 years ago in Madison, Wisconsin, where we started working with recyclates. And in the US, it's even, we had jokes, people said, in Germany, do you really collect trash in your home for days and weeks, and then you walk to the corner of the block and put it somewhere? Wow, that's a lot of effort. And so that's what the US is. That's also the reason why we wrote the book. But the need in the market is really adopting more recyclates and increasing the quality. We conducted customer interviews if DSC and an automated solution would be interesting. And what we found, a little teaser, is that what is interesting to the industry is a method where they don't need to train a PhD and hire a PhD to operate it. So that's why we said, okay, we need something that's completely automated. You only have CapEx, so you invest in a DSC, but then the operation is more or less without additional cost. Then the next step was data collection. So getting enough DSC data that we can train AI models, the training itself, working with alpha testers who got access to the software very early, and then we started to go in a feedback loop. Data collection, model training, alpha testers, and we are actually going to continue that as we continue the development of the software. So the market need is really a quick and inexpensive composition analysis, because we want to classify recyclates regardless if it goes in mechanical recycling or chemical recycling. We need to know the feedstock, otherwise our products, in chemical recycling, our reactors are going to suffer if there's chlorine in it, from PVC, for example. We think we can enhance sorting quality and efficiency when people do quality control and see if the sorting was sufficient. We think it's very important that we're able to provide material data sheets just like we're used to. And even so, that might be smaller batches, that is something that will increase the confidence in recyclates. And finally, predict processability and the final product quality. The key customer insights we got from the interviews was that DSC is already the technology that everybody's looking at, because we don't have the problem with dark and multi-layer material. There is a need for precision. So in injection molding, and depending on the material you're using, you might be able to tolerate 5% of contamination. But if you think of a thin film, then 1% is already the amount that's possible. Otherwise, your product will be failing already during processing. Something that was very surprising, I guess, we were so focused on asking the interviewees how worried they would be about us offering this as a cloud software. Because we still knew from others that, oh, cloud, no one wants to use it. No one cared. What they were obviously very concerned about is, what does it mean if we trust a result that comes from a machine learning software where we don't know what it does? And we haven't completely solved this. It opens up a big discussion that we hope we can be a part of, because we're learning so much. How do you even standardize around something that was an output of machine learning, and we have no other means of checking other than chromatography methods, everything that's very expensive and time consuming. So a priority for us was to understand what the machine learning does. And my data scientist colleague, when I said, do you think it already knows that this little bump in front of the big curve, that it knows that's LLDPE? And he said, sorry, we can't ask. That's just the reality. We just have to provide a lot of data. And what we also think is that we can increase the recyclate content that a lot of industries are looking at and asking for, and that we will be able to contribute to a higher use of recyclates. And now most of the talk is going to be about the data collection, how to get reliable data. It's not just, that's a spoiler, it's not just how many DSC curves we have for training, but also have high quality ones. So we need reliable high quality data of known polymer mixtures. So we compounded mixtures with known percentages together and gave that as input. And as you will see, there's some expert knowledge needed in order to understand what the relevant effects are and what data needs to go in. So that's the little spoil with what a DSC result looks like. I show this on the graph over here. From a DSC result, we get the DSC signal as a function of temperature, and what we can typically learn from it, this is a PET material, so that's semi-crystalline. We can learn something from this little step in the curve that's related to the glass transition, and the higher that is, the more amorphous is a material. And then we learn from this peak. So we learn from the peak temperature, so the highest point. We learn from the onset, endset, the area underneath. All of these features of the curve are relevant in order to understand the fingerprint of a material. And families and blends produce distinct patterns that we can look for. But what I want to talk about is what can all be influencing factors on a DSC curve. The first I show here is the influence of sample mass. It depends how much you put in your machine. For one and the same material, a low mass will produce a more narrow peak, a high mass, a more broader peak. Broader peaks are bad for us because overlapping peaks will be harder to distinguish. So too high, the peak becomes too broad, too low, we have errors. It's one of the same material and it can produce this difference in a curve. The next is effect of heating rate, also messes things up. You see here also in the schematic, low heating rate in blue, high heating rate in red. Again, it's a DSC of one and the same material, but depending on what parameters you use for the measurement, your curve will be very different. And I think those of you who work with machine learning probably already think about, okay, if you have such varied data, how do you train a model? And yeah, that's really what it is. Because of that, we defined mass and heating rate for all of our training data, that's set. And that also means the rate and mass must match of whatever we want to analyze. That's the conclusion out of that. Last, effect of cooling rate, similar to heating rate. This is also a schematic of how that would look. A faster heating shifts and the peak shape broadens. And so also for the cooling, we have defined 10 Kelvin per minute for the training data. And if you want to use Quantify, you have to upload 10 Kelvin per minute data. This is a combination graph that shows if I had mass and the heating and cooling rate mixed up, I could again get very different curves. And data training would be extremely difficult. So consistent training data is key, and I think that is not just from DSC data. We have that in mechanical testing. The speed at which you pull has an effect on your results, and that's why, in my personal opinion, after doing this now for quite some years, we can't just data mine technical literature, because we hardly ever get all the information we need to categorize the data and say the DSC data we can use for training or not. So we really have to create good data, and I think we heard that in other talks as well. I'm just talking about a specific data problem. And the training data and the comparison data need to match. So what you want to analyze, the unknown mixture, also has to be measured with 10 Kelvin per minute and 10 milligrams of mass. Sorry. No, that's what I wanted to show. So this shows great variability. Now I talked about the influence of the measurement. Now I'm talking about the influence the material supplier has in generating materials that are very fit to one purpose. This is showing the melting peak of 20 polypropylenes, or 25. And you see they all look different. The area under the curve is different. The peak can be here or here, so we have a variability of up to 10 degrees C in that peak temperature, and we have a spread of enthalpy between 73 and 114 of the data we had. So what does that mean? It doesn't mean it's an unsolvable problem. It means diverse training data is very important. We have to more or less show in the training data the diversity that exists in polypropylene, and that's where expert knowledge comes in, talking to the material suppliers, knowing what the edge cases are to train properly. And then a question that we have already gotten from customers and early people who are interested, also at our booth, how can you train with mixtures of virgin material when recycled material is actually what we're looking at, and that's degraded and so on? For a lot of plastics, there's a relatively simple answer. The degradation doesn't show too much variability in a DSC curve. So in the thermal fingerprint, the effect is not so big. I talked to someone, David is also here in the audience, about nylons. That will be different, and we haven't fully started with the nylons yet, but for PP, you see this example. The different DSC curves show material that was 6 times extruded compared to the virgin, and the thermal fingerprint doesn't change. So a learning was definitely that the spread between grades is much more important than the spread we get through reprocessing. And now I only talked about single component materials, but I introduced what I want to talk about is talking about blends and unknown compositions. So what do DSC curves of blends look like? I divided in 3 categories: the easy, the moderate, and the very extreme and difficult or even impossible to solve cases. Here you see an example of LDPE, maybe with a nylon 6 barrier layer. Super easy to distinguish because LDPE is this peak, nylon 6 is this peak, very far away. We can easily distinguish between the two. The actual composition was 96 and 4%, and with the DSC analysis and knowing enthalpies, we got very close to that. Overlapping peaks, I already mentioned that once. That's where the problem starts. This, again, is still an easy case of overlapping peaks. You see that here. Overlapping means, in the case of the purplish curve, we're not getting back to the baseline. So we have to know where do we actually say this first material ends and the second begins. That's where some knowledge is needed. So we need to separate that by enthalpy. And now Mission Impossible is really when material co-crystallize, and that's the case when LLDPE and HDPE are put together in the waste stream. Then we get, I show here a curve for the pure HDPE, in red for the pure LLDPE, and in between. But you only see 4 different curves and no different peaks inside of a curve. That's because it co-crystallizes and it doesn't create 2 peaks that we can separate. So it's very important that we use calibrated blends and that we label them properly. And that's a hard learning. Maybe I should say that we trained the model, and then we added more data, and the model got worse. So, that was not what we expected. It was a lot of data. And then we realized that during the data processing, some mislabeling had happened, and PP was classified as HDPE and vice versa. And then the model really didn't know what HDPE and PP looked like, because in one data set, it said HDPE, in the other it said PP. And once we found that mistake, it even improved. That was the intention we had. And the AI advantage is really when it comes to these very complex peaks. That's an example of LLDPE, LDPE, HDPE, and PP all mixed together. So it's a peak and valley. It looks like even like a nice painting, heating curve, cooling curve. The AI or the machine learning that we implemented interprets the subtle variations we have across the data sets and allows us to distinguish between the materials. So then what were our learnings for model training? We have to really specify how our customers need to measure. We can't just say measure it however you want. We set it to 10 Kelvin per minute and 10 milligrams. The labels need to be set, then features and curve embeddings need to be trained. And for quality, right now we're reporting a root mean squared error, a value that tells you how good the model predicts each of the polymer classes. LLDPE is still a little more difficult. For those of you familiar with LLDPE, it can either show 2 peaks and in some grades 1 peak. That means we need more LLDPE data still. But label integrity, in our case, is much more important than the data set size. And the other thing, you know how many polymers exist. It's an impossible task because we couldn't produce a software that cost $20,000 a year to use or something like that. The more data we need to input, the more expensive the software gets, and then also for the customer. So we need to have a balance. And the way we approach it, I hope that was something you could see. The way we approach this is really having experts like me, and we work with development partners, look at the data and find the most diverse data sets that represent the polymer class. Then the development journey that we were on, and we're still continuing that because right now the software only includes polyolefins, and we have a roadmap to have all packaging material and eventually the nylons and PETs and PPTs. We continue with alpha testers, and they always have a test version, and they upload their data and they give us feedback. And however, as we launched it today, we also invite potential customers to become part of that iteration. And we always find a deal if that's necessary. If you're not an alpha tester but already want to be a customer, we're very interested in the cases where it doesn't work, where it breaks, because we know that means that extreme case or that edge case we haven't implemented yet. So why I'm also here today, I want to say I'm open to a dialogue and willing to work with the customers on getting this right. This is how the software looks. You get a polymer family ID and a blend fraction estimate. It literally just gives you a table. And we add some visualizations because the alpha testers had some requests in the customer interviews. We have right now typical validation errors between 1% for these easy cases, and 3 to 5% for the extreme cases. Like LLDPE and HDPE, the error is larger. And I hope we can build the reference together. I had this little girl that was screaming at the trash, and I was very fortunate to find this image now of a girl that looks into a bright future. We're looking for partners that are willing to share data of calibrated blends. So far, we have mostly worked with universities and research institutes that do that in their recycling studies. Interested in pilot projects in packaging, automotive, and electronics and construction. And also interested in joint publications on the topic of machine learning with DSC or in recycling. What we think the value will be, compounders and processors should gain confidence in recyclates to use them and make plants predictable and stable. For OEMs to get transparency and traceability, that they know what's in the project from start to finish. And hopefully everybody benefits because we can adopt recyclates more. So what's already in the data or in our material are the polyolefins, as I said. In January, we hope to have these included. We're already starting with the nylons because they give me still some headaches. And what we also already have started is filled systems, because fillers also are not the easiest when you have already changing enthalpies through different grades. So my personal conclusion is that AI won't solve recycling alone, but it's a powerful equalizer, and tools like Quantify that we developed, and you can probably see it's a passion project that I convinced our management that we should do. We make advanced analysis accessible, because we want people to only need to invest in the instrument and be able to run it and learn while you're using it. And what is still an unknown, because we have implemented more materials that we're already selling, and it works well. But we don't know, once we have 25, 30 polymer classes in there and we see all the overlaps, if for certain combinations it will be more tricky. But I hope that improved sorting will follow along. We talked about that earlier. There's already a lot of smart sorting. And if sorting already gets better, then it's more predictable what could be in a mixture. And that probably narrows what we actually have to analyze. So if you're interested on a touch screen to see the software, look at more complex materials than what I just showed in the screenshot, visit us in Hall 11, booth A48 to see it in action. And with that, I'm at the end of my talk, and I'm happy to take any questions.
Thank you so much, Natalie, for giving these insights and also showing where you're at and where also currently the status and limits are. So we have a couple of minutes left. Are there questions to Natalie regarding the DSC program, the software?